This section outlines predictive analytics and reporting to a global optimizer, including anomaly detection and maintenance status. Operationally, this connects operational sensing to decision-making. The system can recommend actions and also flag when equipment health threatens schedule feasibility. This section introduces an orchestrator that initializes subsystem twins and runs a global optimization loop in 30-second cycles, plus what-if scenario analysis. Operationally, the orchestrator is the coordination layer. It merges subsystem states, produces decisions, distributes them, and keeps a dashboard updated with scenario impacts. Tier 9 maps dual cycling into a quadratic unconstrained binary optimization form, and then applies a quantum approximate optimization algorithm. Conceptually, the idea is to encode the objective and constraints into an energy function and use a quantum circuit to explore many candidate schedules in parallel, while a classical loop tunes the circuit parameters. This slide shows a cost function expressed with quadratic interaction terms and linear terms. Operationally, the quadratic terms capture pairwise conflicts and dependencies, such as interference or precedence coupling, while the linear terms capture individual operation costs and dual cycle bonuses. This slide shows the parameterized quantum state construction as repeated alternation between problem and mixer transformations. Operationally, depth represents the number of alternations. More depth can improve solution quality but increases computational burden and sensitivity. This figure shows the quantum circuit architecture and a performance comparison idea. The key takeaway is practical framing. Quantum methods are presented as a roadmap for certain combinatorial scheduling regimes, not as a drop-in replacement for all planning. The example instance includes 3 cranes, 8 containers, and 12 time slots. The qubit requirement is described as 288. The circuit uses 2 layers and a classical optimizer described as Kobila, with 150 iterations. Penalties are described as 1,000 for interference, 500 for precedence, and 200 for stability. The reported result is a make span of 28 minutes versus 45 minutes for a greedy baseline, with 6 dual cycles out of 8 operations. This code section defines the quantum optimizer structure and how the number of qubits is derived from cranes, containers, and time slots. Operationally, the core risk is scale. The model grows quickly, so feasibility depends on exploiting structure and sparsity. This section outlines construction of linear and quadratic terms for a QUBO-style objective, including constraint penalties. Operationally, penalty calibration is essential. If penalties are too low, the algorithm returns infeasible schedules. If penalties are too high, the search landscape can become difficult to navigate. This section describes how the quantum circuit is built, including initialization into superposition, layered operations, and measurement. Operationally, measurement sampling means results are probabilistic. You need enough repeated runs to estimate which schedules are consistently good. This section outlines the expected cost evaluation and the classical parameter optimization loop. Operationally, this is a hybrid approach. Quantum execution proposes candidate solutions, while classical optimization tunes parameters to improve the expected objective value. This section describes decoding the best bit string into a schedule and computing metrics like dual cycle ratio and make span. Operationally, decoding must preserve the interpretation of decisions. If decoding is inconsistent, comparisons to classical heuristics become misleading. The practice questions focus on implementation readiness across tiers. You practice defining the Markov decision process state, action, reward, and Bellman recursion. You also practice implementing Bay decomposition and estimating coordination overhead, encoding schedules for a Firefly algorithm and evaluating intensity, building an imitation learning dataset and testing generalization, designing digital twin synchronization with scenario analysis, and mapping constraints into QUBO penalties while estimating qubit needs. Dual cycling converts empty crane movements into productive operations, which can shorten vessel handling time without adding equipment. Tier 1 defines a complete sequential decision model. Tier 2 provides practical decomposition heuristics. Tier 3 and Tier 4 improve performance through meta-heuristics and learning. Tier 5 integrates system-wide optimization, and Tier 9 provides a roadmap for quantum acceleration.